Welcome to Pomodoro Joe for Friday, May 26, 2023. Today we're looking at LeetCode problem 1140, Stone Game 2. This is a medium problem. Alice and Bob continue their games. This is a continuation, okay. So Alice and Bob continue their games with piles of stones. There are a number of piles arranged in a row. Each pile has a positive integer number of stones, piles index I. The objective of the game is to end with the most stones. Alice and Bob take turns, with Alice starting first. Initially, m is equal to 1. On each player's turn, that player can take all the stones in the first x remaining piles, where x is greater than or equal to 1 and less than or equal to 2 times m. Then we set m equal to the maximum of either m or x. The game continues until all the stones have been taken. Assuming Alice and Bob play optimally, they both play optimally, return the maximum number of stones Alice can get. Whoa, this one's another complicated medium problem. Wow, 2 in a row. All right, well, let's put 25 minutes on the Pomodoro timer and we will get started. Okay, so this seems like a recursive problem, but with a twist, because we've got 2 players each taking turns. So we'll start out with our basic recursive algorithm, and then we'll have to make some modifications to it. So we'll have a result, we'll set it to 0 to start, and we will return our result at the end. Next, let's define our recursive function. So we'll just have stone game recurse. Let's see, what does our recursive function take? Well, it'll take our starting index. It will also need our m, and that might be all we need. So we'll start with that. We have the index that we're starting on, and we have our current m. So in fact, we don't need this external result here. We'll just do our recursive call at the beginning here. So we will return our stone game recurse, starting at index 0, and m starts at 1. Okay, so this should be our basic recursive algorithm. Now we'll have some internal result, set that to 0, and we'll return that result here. All right, so what is our base case? Well, our base case is if the index is greater than our maximum index. So let's actually define our maximum index out here. That's going to be the length of our piles minus 1. All right, so here, if our index is greater than our max index, we return 0. There are no more piles to take. We have 0 stones. All right, next, we've got our base case, so let's do our recursive cases. And how many recursive cases are there? Well, there might be a lot, because we can choose our first pile, second pile, third, fourth, all the way up to the mth pile, or actually 2 times m pile. So let's define our x, actually. So we'll have some minimum x. And that's going to equal 1. And then our maximum x, well, that's going to equal 2 times our m. Okay, and now we can go through every one of these min to max x piles. So for our current x in range, we can go from min x, and we can go all the way up to and including our max x. So we'll do max x plus 1 to include it. So that's our current x. Now we have to actually reconstruct our index out of this x. So this is going to be a little bit tricky. So we have a current index. Well, that's going to be our index plus this x. But since x is starting at 1, and our current index, this index that we pass in, could actually be our first index, the first pile that we take, we actually need to decrement this by 1. So our current index will be this index plus x, which starts at 1, so it'll be 1 minus 1 to begin with. So we can end up just getting our index back out. And then our next index, actually, there might be a problem here too. Our current index could exceed our max index. So before we check our next index, let's do a check. If the current index is greater than our max index, we'll just continue for now. We might want to return there, but for now we'll just continue. We don't want to do anything that's above our max index. Okay, so then we have our next index. and that's going to be our current index plus 1. So this is for our recursive call. And then we'll also have a next m. So that's if we do a recursive call, we'll pass this next m, and that's going to be the max of either this x. Actually, what do they say here? Max of m or x. So that's going to be the max of m or our x. So now we can make a recursive call. So this is the recursive option. We will do our stone game recurse, and we'll pass in this next index and this next m. Great, but there's a problem. So this is our standard recursive function. We're going to basically grab some value out of this current list, then we'll recurse on some future values. But this next index, this whole next option, this is Bob's turn. This isn't Alice's turn. So normally we'd be like, okay, we'll grab some stones. Actually, we didn't grab the stones. Let's do that. So let's grab these stones. So what do we call it? Like, I'll just call it stones. So we've taken 0 stones so far. Then when we get down here, we'll take some stones at our current index. So our stones will increase by the number of stones at this pile. So that's going to be piles at this current index. So we're going to grab the stones at this index, and then we'll recurse on the next index with the next m. And in a normal situation, if this were just what's Alice's best score if Alice is the only player, we would do these stones plus the optional stones from every single possible option and find the maximum value. But the problem that we run into with this problem is that this stone game recurse function is actually Bob's turn. So whatever value we get back for this option, this is going to be Bob's score. And that's not really helpful to us. So the trick to this one is trying to figure out how do we use Bob's score to give us Alice's score. Okay, so here's my plan. We're going to grab some stones. Alice will grab some number of stones, these stones here. Then it's Bob's turn. Now we know the total number of stones in all of the piles. So on the very first turn, Alice goes, it's her first turn, but then it's Bob's first turn. And Bob is going to try to maximize his score. So whatever Bob's score ends up being, then Alice's score from the previous turn will just be the total number of stones that we have in all of the piles minus Bob's score. So the number of stones that Bob was able to get. So this is kind of thinking backwards, where on the very first turn, we don't know Alice's score necessarily, but we know that her score will be the total number of stones minus whatever Bob's score is on his first turn. So we'll have to calculate Bob's score here, this option, and then we'll have to take away that score from the total score, the total number of stones. Maybe I'll call this Bob's score. So we'll take Bob's score and we'll subtract it from the total number of stones to get Alice's score for this turn. Okay, so let's see. Let's just do that here. So that's going to be, let's see, the total number of stones. Well, that is going to be just the sum of the piles. And then we'll take away Bob's score. So Alice's score here is all of the stones minus whatever Bob's score is on his first turn. That's our recursive call. And now our result will just be whatever is better, our current result or this new score. So let's see. All right, so this looks pretty good, but there's a couple things that we're not taking into account. So for Bob's score, now Bob's score is going to be a recursive call, which means that we're still using the total number of piles minus Bob's earlier score. So if we're looking down the line, we have Alice and then Bob, and then Alice and then Bob. So on our recursive call to the very last call, whatever score we return here, so our very last score we return 0. That very last score returns 0, which means Alice's first score, or Bob's first score, depending on who has that last move, is going to be all of the stones minus 0, which is of course going to be the winner, but that's not quite Right. We don't get to take all of the stones into account. We just have to take the remaining stones into account. So by the time we get down to the very last case, this returns 0. However many stones were left before we had that last call, that becomes our base score, or our base number of stones. So we can't just use the sum of the piles for every single recursive call. We actually need to keep track of how many stones are left in our remaining piles. So let's add a new factor here, a new argument. So we'll have the total stones, or remaining stones. Yeah, let's do remaining stones. Okay, now we're getting somewhere. So in here, we'll have to pass in our start stones, which is just the sum of the piles. So this is how many piles do we have, or how many stones do we have in total. So our remaining stones start as all of the stones. Then when we get down here, we don't have all the stones anymore. We have to pass in something new. So let's see, Alice just took out some stones. So our remaining stones are going to be the remaining stones minus the stones that Alice just took out. So let's see, we'll have to add remaining stones, or maybe I'll call it new remaining stones, our next remaining stones here. That'll keep everything clean. So that's going to be our remaining stones minus the stones that we just took. And then here we call next remaining stones. Then we have Alice's and Bob's score, but Alice's score isn't all of these. It's just whatever was remaining. So that's going to be the remaining stones minus Bob's score. And then we can return Alice's maximum result. Okay, let's give this a shot and see if it works. That works. I'm actually a little bit surprised by that. Okay, so this does work. We're going to find our x values first, and we can go from the min x to the max x. Then once we go through all these min x and max x, we figure out our current index. And we have to do a little bit of careful calculation here that we don't exceed our bounds. So we find whatever pile that we can take stones from, we grab those stones, then we'll figure out our recursive call for Bob's first or next move, find out Bob's maximum score. So the nice thing about this is we're always returning the maximum. So each time our players are trying to play optimally. So we're returning the maximum score that Bob could get so that Alice can take whatever remains of the stones and take away what Bob was able to get from his max score. And then we'll return the maximum of the scores either, then we'll go through all of our options, or for every option that we have, we'll just find the best option so far. Okay, let's submit this. We are not doing any type of caching, so this probably won't run in the runtime we need, but simple fix, so we'll just see how it goes. Yep, time limit exceeded. Well, we'll grab this test case, and we'll just use caching. So we'll just use our functool cache. So from functools, import cache. We'll just cache that value out here. Let's see how this goes. Okay, that seems to work. Let's see if we can pass all the tests. All right, and we pass. We don't do great, we do all right. We beat 58% for runtime and 28% for memory, so that's not too bad actually. A couple things we could do to speed this up. I put a lot of these helper variables in here. A lot of this could be condensed and cleaned up. So that's one thing we could do. Another thing we could try, instead of doing caching, we could do our own dynamic programming. Actually, let's do that. I'll show you how to do that really quick. So this is a simple dynamic programming. Maybe not the optimal, but a simple way to do it. So let's not do this functools cache. So instead of caching, we'll do our own DP. So this is going to be DP, and we'll make it a dictionary. So the key into this dictionary will be essentially our arguments into this function, and the value will just be the return value. So let's start here. Very first thing we'll do is we'll make a key. So our key, and that's just going to be a tuple of our arguments. So the index, the m, and our remaining stones. Now, if that key is in our DP, then we just return. So if the key is there, then we'll return DP for this key. So this is how I usually do DP, simple DP. Create a key. If it's in our database already, or in our DP, in our dictionary, then we just return that value. We don't need to do anything else. Otherwise, let's just look for all of our return values. Any place we might return, let's look for those, and we're going to set our DP for that key. So we still have our key, so the DP of the key here will be 0, and we'll return 0. Next return is down here, so we'll just set our DP for this key equal to the result, and then when we return the result, we'll just return our DP for that key or return result. They're about the same. So now we're setting our DP for all of our results to this particular set of inputs. Let's run this, see if we can pass. Still passes. Let's see if we pass all the tests. Now this is without our caching, but with dynamic programming. And we pass. We only beat 53% for runtime, 27% for memory, so it's about the same. It's a little bit of a hit. We actually didn't do quite as well as the Python caching decorator. So it doesn't always give us the best answer. All right, again, we can go in and clean a bunch of the stuff out. We could do an early return here. That might help. Actually, let's do that. So we'll just return result here. And we'll also set our DP to that result. Again, any place we return, we have to set our DP. Let's see if that works. Okay, let's see, that might save us a little bit. We're going to shortcut a couple of these recursive calls. 54% doesn't really save us that much. A couple other things we could do. This max, and this max, anytime you use a max function, consider writing your own. So in this case, instead of using max here, we'll just say it's m if our m is greater than our x, else it'll be x. So if m is greater than x, we'll use m, otherwise x. Same thing down here. We can do this max. Instead of this, we can say result is equal to result if result is greater than Alice's score, else Alice's score. Okay, let's see how that goes. All right, so this might actually save us a lot more than even doing the DP, and it does. So now we're at 61% for runtime and 25% for memory. Not too bad. We'll go back and let's, instead of using this DP, let's go back to our cache here. Okay, let's see if this still works. All right, I didn't do the import, so it looks like I guess I don't need to import from FuncTools anymore. That's nice. 67%, so our DP is worse. So that's the best one so far. 67% for runtime, 25% for memory. And then finally, we can go through and clean up a bunch of these little things like this next index. Let's see, we have 7 minutes. Yeah, let's do some cleanup. Why not? So this min x being 1, we don't actually use that anywhere except for here, so we can get rid of this guy. Max x, that might be nice to keep around. What else can we clean up? Also, we have current index is index plus this x minus 1. And then we do the next index is current index plus 1. We already did a minus 1 here, so we might be able to do a little bit of cleanup in there. Okay, we only use next stones down here, so we could actually just pass this in. That saves us a little bit. Next m, again, we only use next m here, so we could put that in. That would look a little bit weird in the function call, so I might keep that one. But the next index is just current index plus 1, so we could actually just replace that in here. We only use it here. Clean that up. Now Bob's score, let's see. Bob's score we only use here. So we could actually replace Bob's score with this. Get rid of this, but now that's a really long line, and we only use Alice's score here. So we could just replace this with result. That still makes a long line. I'm trying to think if there's an easier way to do this. Let's say option, go back to my op. So now this is our option, and the result will be result if it's better than our current option. Otherwise, we'll use the option. Okay, this is starting to get a little bit cleaned up. This is starting to look pretty good. All right, let's see if this still works. I might have messed it up. Still works. Let's see if that cleanup helps us at all. Fewer lines to parse, fewer variables to use. Not really. 68% and 25%. It's a slight improvement on the runtime, but barely. All right. I don't know. I'm running out of ideas here other than to maybe minimize some of these names, which I don't really feel like doing today. I've had a long day. So I think that'll be it for me. All right. Quick recap on, let's see, this final answer here. So this one is very weird. This is a harder medium problem. But the main idea here is that we're going to go through, and instead of just trying to calculate Alice's score, we're going to calculate Alice's score in terms of Bob's score. So that means every step along the way, we're still trying to find a maximum score, but we can use the maximum score of the next person's move to calculate our maximum score by using the remaining stones and subtracting their score from that remaining stones count. It's a weird one. Yeah, I recommend just check this one out. I'll leave a link to my code in the description, and yeah, take a look at this one. It's definitely worth trying. Try this one on your own. This is one of those ones where it's like, I recommend trying it because it's not intuitive and it helps to sort of work through the problem. Okay, well that's it for me. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.